René Descartes once said, "I think, therefore I am." But in my case, I say, "I think, therefore I move." Now, to provide a bit of context, my team has designed a brain-controlled wheelchair called Brainchair. Simply think of the movement and watch yourself move to wherever you want to go. Now, the whole reason why we created this is for those who are unable to move themselves. More than 2 million people in the United States are affected by diseases such as ALS, brain or spinal cord injuries, cerebral palsy, muscular dystrophy, multiple sclerosis, and numerous other diseases that impair muscle control. Many of these people are confined to their wheelchairs. Some may be lucky enough to be able to control their movement using a joystick. However, there are still many who cannot use a joystick, eye tracking systems, or head movement-based systems. However, a brain-controlled wheelchair can solve this issue and provide the freedom of movement for the physically disabled. The brain-controlled wheelchair allows the user to control a wheelchair solely using an open BCI headset. The headset is an EEG device, which you see here, that allows us to read brain signal data that comes from neurons firing in our brain. When we think of certain movements, certain neurons in our brain will fire, and we can collect this EEG data through the BrainFlow API in Python, which allows us to stream, filter, pre-process the data, and then finally pass it into a classifier. For data collection, we collected our data using the BrainFlow API streaming functionality and stored it in a CSV file. This is very useful for training our machine learning model later on. And we needed to collect enough data and label it to classify whether the person is thinking of pushing or going forward, pulling, going back, going right, or going left. For signal preprocessing, we applied a notch filter at 60 and 120 Hz to remove power line noise. We also apply a Butterworth filter to smoothen the drop at the cutoff frequencies. This helps ensure we get clean data before we proceed. At this point, we can pass it into our convolutional neural network, and you should note that each electrode is very similar to like a pixel in like an image, which is why we use a CNN, and I think it's perfect for this task, just because everything's spatially distributed, very similar to how pixels in an image are spatially distributed, and you can get data from each pixel as well. Now, once we have the CNN classify the signal, this signal needs to be passed to the hardware somehow. So on the hardware side, we actually send the classification or the signal through Wi-Fi to a Raspberry Pi, which controls the movement of the wheelchair. In our case, since we didn't have a motorized wheelchair on hand, we used an RC car as a replacement. We simply hack together some transistors onto the remote, which connects to the Raspberry Pi. To communicate with the Raspberry Pi, the computer publishes to an MQTT topic for the Raspberry Pi to receive. Here's a video of the wheelchair in action, along with the OpenBCI GUI to visualize my brain signals as I control the RC car. Note that we used an RC car instead of a motorized wheelchair because we did not have a motorized wheelchair on hand, once again. But anyways, on the left, you have the actual OpenBCI GUI, which visualizes all 8 channels of data. So there's 8 electrodes on this headset, and as you see on the left is the stream for, like real-time stream for this data itself. And on the right, obviously, you see our wheelchair moving around with our paper person on it. It was difficult to obtain some of these things here. So these are some of the barriers we faced. The first thing was obtaining clean data, because it takes a lot of effort to make sure that we get clean data and that there isn't other noise. So for example, even if you blink, that can throw things off. Another thing is actually training our machine learning model, because we need much more data than we currently have, and we need much more time to actually train our machine learning model and good classification accuracy. And finally, another barrier is hardware. So actually getting the motorized wheelchair is, we don't have the money for that, which is why we just stuck with an RC car. For further improvements, one big thing is improving the model accuracy itself, because if this was used in real life, we need to make sure that people are safe and that there aren't any accidental like moving forward or they don't accidentally move back either. Another thing is kinematics, so making sure the movement is smooth, because right now, as you see, or as you saw with the RC car, it can be a bit jerky. And finally, we also want to add another system for manual control to make sure maybe they have a caregiver or someone else to make sure that nothing goes wrong in case the wheelchair is defective for some reason, or just to control them in any sort of dangerous environment. Finally, for further application, really this is for people with physical disabilities who can't control their wheelchair using a joystick. And I think the brain-controlled wheelchair gives them their freedom for their own movement and just gives them their freedom back to their own life and for them to be themselves. So yeah, that's all I have. Thanks for listening.